So our next algorithm is heap sort. So in heap sort, we will see what is heap, how heap is created, what are the types of heap, MinHeap, MaxHeap. Okay, so how we do insertion in heap, how we do deletion in heap, and what is Heapify method. That is very important method. Okay, and after all this, we will see what is heap sort. So without understanding these things, we cannot understand heap sort. So we need to understand what is heap. Okay, so let's start with what is heap. Now, what is heap? Heap is nothing but complete binary tree, right? So what is complete binary tree? Basically, what is tree? Tree is a hierarchical structure in which we have, let's say, parent, and then we have child. So if a element have two child, then it is called binary tree. So it is binary tree because it have two child. Now what is complete binary tree? It is a kind of binary tree in which at all the levels we have two child, like this. Okay, at every level we have two childs. So it have two child, this and this. It have two child, this and this. It have two child, this and this. This is a complete binary tree. But there is one more condition in complete binary tree. It says that in last level, it can be completely filled or not. Like this is also complete binary tree, right? This tree is also complete binary tree, right? But this is not a complete binary tree. So complete binary tree says that last level may or may not be completely filled. So last level may or may not be completely filled. Now second rule says that the elements will be filled from left, Okay, so this is not a complete binary tree. Now let's see some more examples. So let's find out which are complete binary trees and which are not. So let's see this tree. Is this a complete binary tree? Yes, it is a complete binary tree. Why? Because it is not completely filled and also we have filled from left. So it is completely binary tree. Now, is this a complete binary tree? No. Why? Because we have not filled from left. So it is not a complete binary tree. Is this a complete binary tree? So we started filling from left onwards. So this is also complete binary tree. Now, is this a complete binary tree? Yes, this is also complete binary tree. Is this a complete binary tree? See, we have not filled the left one, right? Also at every level we have not filled this one also. So at every level we will fill left, then we will fill right, and then go to next level. So this is also not a complete binary tree. Is this a complete binary tree? No. Why? Because we have not filled the left one. So the order is we will first fill the left one, then fill the right one, and then we'll go to the next level and start filling from left onwards. Okay, so is this a complete binary tree? No. Why? Because this level is completely filled, but here we have not filled this. So first we will fill this, then this, then this, then only we can fill this. So this is complete binary tree, this is not, this is not, this is not. Okay, so we have understood that what is complete binary tree. Now move forward. So heap is nothing but it is a complete binary tree structure. So let's take an array. Let's say I am taking 3, 2, 1, 4, 5, 6. Okay, and let's start from index 0, 1, 2, 3, 4, 5. Okay, so these are our array elements. and these are our index 0, 1, 2, 3, 4, 5. Now, if I want to draw a complete binary tree of this array, how we can draw that? So we have 3 at root, right? So in the left we start filling. So in the left 2 will come. In the right 1 will come. Okay, now go to the next level. We will start filling. So we have filled 3, we have filled 2, we have filled 1. Okay, now remaining 4. So we will fill 4. Now go to the right of 2. We will fill 5. Okay, so we have filled left, we have filled right. Now go to the 1. So in 1 we will fill 6. Okay, so this is a complete binary tree. This is the complete binary tree of the given array, right? So how we can create a heap from it? Is this a heap? It is a complete binary tree, we know that, but is it a heap? No. Why? Because heap have one more property. Heap is complete binary tree, but it also contains one more property. What that property is? So heap can be either MinHeap or MaxHeap. Now what are these terms? MinHeap and MaxHeap. What are these? So let's understand using an example. So I know how to draw a complete binary tree. Okay, so let's say I draw a complete binary tree. Let's say I take 1, then 2, then 3, then 4, then 5, then 6, then 7. So it is our complete binary tree, right? We know that it is our complete binary tree, but it also contains one more property. What is it? Can you find? See, we have 1, it is parent, and 1's child is 2 and 3. So 2 is a child of 1. Child is greater than parent, right? So 2 is greater than 1. Let's write this property. Child value is greater than parent. Okay, let's keep this property in mind. So let's start traversing the tree. So in this tree, 2 is a child of 1. 2 is a child of 1, and 2 is greater than 1, right? Now come to the right. 3 is a child of 1. 3 is a child of 1, and 3 is greater than 1. Okay, so child value is greater than parent. Now come to the next level. So come to this level. Come to 2. 2 is a parent for 4 and 5. Now 4 is greater than 2. So it is fulfilling the property. It is fulfilling this property. Now come to 5. 5 is greater than 2, right? So it is fulfilling the property. Now come to 3. 3 is less than 6. 6 is a child of 3. So 6 is greater than 3. So it is also fulfilling this property. Now come to 7. 7 is greater than 3. So 7 is also fulfilling this property. So this is nothing but our MinHeap. This is our MinHeap. Let's write it. This is our MinHeap. Okay, so what MinHeap is? MinHeap says that at every level, the parent's value will be less than child value. Okay, at every level, parent's value will be less than child value. So in this tree, we have seen that parents at every level, at this level, this is the root level. At second level, parent value is less than child value. Okay, so come to this level. At this level, 2 is less than 4, 2 is less than 5. 3 is less than 6, 3 is less than 7. Okay, but there is one more case. Are these childs are related to each other? No. These childs have no relation with each other. They only have relation with their parents. What does it mean? Let's say if I interchange them, Let's say if I interchange them, then also it is min heap. Let's say if I interchange them, this will be 4, this will be 4, this will be 5. This is also min heap, right? So let's take few examples of min heap. Now let's take these examples and find whether these are min heaps or not. So come to this first one. Is this a min heap? So let's see. 2 is a child of 1 and 2 is greater than 1. Okay. 5 is a child of 1 and greater than 1. Okay. Now come to this level. 6 is a child of 2 and greater than 2. Okay. 3 is a child of 2 and greater than 2. Okay. 7 is a child of 5 and greater than 5. Okay. 8 is a child of 5 and greater than 5. Okay. So this is min heap, right? But here you can see 5 is greater than 3. 5 is greater than 3. But 5 is a child of 1 and 3 is a child of 2. So we will see this subtree only. This subtree follow min heap. This subtree follow min heap. So this complete will be min heap, right? This element and this element have no relation with each other. We only have relation with the parent of those child. So this element and this element have no relation. This is a min heap. Okay, come to this one. So 5 is a child of 1 and 5 is greater than 1. So this follows the property. 2 is a child of 1 and 2 is greater than 1. So this also follows the property. 8 is a child of 5 and 8 is greater than 5. This also follows the property. 9 is a child of 5 and greater than 5. So it also follows the property. 3 is a child of 2 and 3 is greater than 2. It also follows the property. 4 is a child of 2 and 4 is greater than 2. So it also follows the property. So this is also min heap, right? We only have relation from parents and child. In child we have no relation. 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 Okay, now come to this one. So 8 is a child of 1. It follows the property. 3 is a child of 1. It follows the property. 5 is a child of 8. Does it follow the property? Does it follow the property? No, right? So this is not min heap. Even if any child doesn't follow the property, then it will not be a min heap. Now come to the next point. Next is our max heap. We have studied about min heap. Now what is max heap? Max heap says that at every level, the parent's value will be greater than child value. Okay, at every level the parent's value will be greater than the child value. So this will be our max heap. Now let's take an example. So let's say we have 7, okay, we have 6, we have 5, then we have 3, we have 2, okay, let's say we have 1 here. So this is a max heap. How? 6 is a child of 7 and 6 is less than 7. So 7 is greater than its left child. Now check to the right child. So right child is 5. 5 is also less than 7, right? So this level follows the property of max heap. So let's see at this level. At this level, 3 is a child of 6 and 3 is less than 6. So this fulfills the property. Now come to 2. So 2 is a child of 6 and 2 follows the property of max heap. So this also satisfied. Now come to this. 1 is a child of 5 and 1 is less than 5. So this also follows the property of max heap. So at every level, the value of parent is greater than child. The value of parent is greater than child. And it is greater than both the childs. It's not the case that it should be greater than only one child. In any case, if the child value is greater than parent value, then it will not be a max heap. Okay, so this is example of max heap. And in MaxHeap also, the childs are not related with each other. They are related with the parent only. Okay, they are related with the parent only. Till now, we have seen what is heap, what are the types of heap. There is MinHeap, there is MaxHeap, and by default in heap sort, we use MaxHeap. Okay, so let's take an example. Let's say we have an array which contains 5, 4, 1, 3, 2, 6. So this is our array, and the array indexes are 0, 1, 2, 3, 4, 5. So if we create our heap, so this will be parent, okay, and its index will be 0. Now the child of 5 will be 4 and 1, and its indexes are 1 and 2. So if we are taking zero based indexing, if we are taking zero based indexing, then let's say parent is I and its left child will be at 2 into I plus 1, and its right child will be at 2 into I plus 2. So here our I is 0, so left side will be at 2 into 0 plus 1, that is 1, and right side will be at 2 into 0 plus 2, so that will be 2. Okay, so if our parent is at index I, our left child will be at index 2 into I plus 1, and our right child will be at 2 into I plus 2 for zero based indexing. If we have one based indexing, then let's say parent will be at I, the left child will be at 2 into I, and the right child will be at 2 into I plus 1. Okay, let's say we have 5, so its index is 1. Now its left child, let's say 2. Okay, it will be at index 2, and right child, let's say 4, it will be at index 3. So if you put the value of I, that will be 1, so left child will be 2 into I, that is 2, and right child will be at 2 into I plus 1, that will be 3. Okay, so this will be our tree for one based indexing. Now why I'm telling this? Because that will be help in insertion and deletion operation. Okay, so let's start our insertion operation. So first, let's say we are doing insertion in MaxHeap. Why MaxHeap? Because by default we use MaxHeap in our heap sort. Okay, let's say we have array elements like 5, 2, 1, 3, 4. Okay, and I want to insert in the MaxHeap. I want to insert these elements in the MaxHeap. So how I can do that? First, I will insert 5. Okay, I can insert as this. Now next I want to insert 2, so I will insert in the left child of 5, so it will be 2. Now after inserting, I will check the property of MaxHeap. So 2 is less than 5, that means our parent is greater than our child, so it follows the property of MaxHeap. Now insert 1, so I will insert 1 at right of 5. Okay, now 1 is less than 5, right? So parent's value is greater than child's value, that means it follows the property of MaxHeap. Okay, till now it is okay. Now we want to insert 3. Okay, so let's insert 3 in the left of 2, and 1 was there, right? So we have inserted 3, but check this, 3 parent is 2, but 2 is not greater than 3. 2 is not greater than 3. That means it doesn't follow the property of max heap. So what I will do, I will swap them. I will compare and swap them. Okay, so let's swap them. This will be 3, this will be 2. Okay, now again, after swapping, I will again check 3 with 5. So I will again check till my root. I will start from my leaf and check till my root. Okay, so now compare 3 with 5. 5 is greater than 3. So it follows the property of max heap. So this tree also follows the properties of max heap. Now I want to insert 4. Okay, so let's move forward. So this was our tree, and now I want to insert 4. Okay, so I will insert 4 here. Now I will compare with its parent. So 3 is less than 4. 3 the parent of 4, but 3 is less than 4, so it does not follow the property of max heap. So what I will do, I will swap them. So let's swap it. So after swapping, let's swap them. It will be 4 and it will be 3. Now again I will check for 4's parent. So I will again check till here. So 4 is less than 5. That means this follows the properties of max heap. Okay, first I will compare this and then I will compare this till my root. So this follows the property of max heap. Okay, now what will be the time complexity of insertion? So let's say I want to insert 7. Okay, so let's say I want to insert 7. What I will do, I will insert at the last index. So I will insert here, I will insert 7. Now what will happen? 1 is less than 7, so it does not follow the properties of max heap. So what I will do, I will swap them. So I will swap them. So this will be 7 and this will be 1. Okay, now compare this one. 5 is a parent of 7, but 5 is less than 7, so it also doesn't follow the property of max heap. Okay, so I will again swap. So it will be 7, it will be 5. Now it follows the properties of max heap. Okay, so inserting 7 takes how much time? See, this is the height of our tree. Okay, so height of the tree is usually log of n in binary tree, in completely binary tree. Okay, so at worst case, the time complexity will be the height of the tree. Okay, so height of completely binary tree is log n. Okay, so one element can take log n times. Okay, so n elements insertion will take n log n times in worst case. Okay, in worst case it can take n log n times, but in best case what can happen? Let's say I want to insert 2 here, so I will insert 2. Now do I need to swap them? No. Why? Because it is in max heap order. So it is in max heap order. So in best case there can be 0 swap, and in worst case we need to swap till log n times. So insertion time complexity is n log n for n elements. For one element it can take log n time. For n elements it can take n log n times. Okay, so this was our insertion in max heap. Now, so let's write our pseudo code for insertion. So let's take a function insertion, and we will take an array. We will take the last index. because we will insert at the last index. Okay, so let's take last index and we will take the value which we want to insert. So take value, and last index will keep on incrementing. Okay, as more as we keep on inserting, the last index will keep on incrementing. So let's pass it by reference. Okay, now what I will do, I will increment my last index. So my last index will be last index plus 1. Okay, and now what I will do, I will put the value at my last index. So I will insert the value at my last index, and I will take a variable index, and in index I will put the last index. Now I will check whether I have inserted at the correct position or not. Now I will check whether the value at my current last index is smaller than parent or not. So I will check till my index is greater than 0. Okay, here what I will do, I will take the parent. So let's take the parent as int parent equals to, I am taking the 0 based addressing. Okay, I am taking the 0 based indexing. So according to 1 based indexing, it will change. So in 0 based indexing, my parent will be calculated as index minus 1 by 2. Okay, so my parent will be calculated as index minus 1 by 2 for 0 based addressing. For 1 based addressing, it can be changed. Now I will check if array at my parent is less than array at my index. If that is the case, then what I will do, I will swap the values at parent and index. I will swap the values at my parent and index. Okay, and also what I will do, I will check for further parents. So now in index I will put my parent and will check for further parent till I reach to root. Okay, if that is not the case, then what I will do, I will simply return. That means the element which I have inserted is at correct position. We don't need to swap, we don't need to change. So I will return it. Okay, so this will be our pseudo code for insertion, and it will take the time complexity of n log n for n elements insertion. Okay, each insertion can take at max at log n times. So n insertion will take n log n times. So I hope you can code it. Now let's move forward to deletion. Okay, so what if we want to delete? So let's take an example. So this is our max heap and I want to delete from the heap. Okay, so what I can do, I will delete from top. I will delete from top. So I will delete the root, and what I will do, I will put the last element at the top. So what I will do, I will delete from top and put the last element to the top. I will put to the top, and what I will do, I will check for further childs if it follows the properties or not. So let's delete the 5. Okay, so after deleting 5, what will happen? I will put 1 here, 4 here, 2 here, 3 here. Okay, so my tree will look like this. Now check for max heap property. So is 1 greater than 4? No. So it is not forming the max heap property. So what I will do, I need to swap, but it should be greater than the childs. The value of parent should be greater than both the childs. So what I will do, I will check if 4 is greater than 1, yes. If 2 is greater than 1, yes. But we need to put the maximum of these two. So what I will do, out of 4 and 2, which is maximum? 4. So I will swap with 4. So 4 will be here, 1 will be here. Now come to next. I will compare 1 with 3. Okay. In insertion, what I was doing? I was checking from bottom to top. Here, what I will do? I will do top to bottom approach. So I have swapped 4 with 1. Now I will check for 1 and 3. So what I will do? 1 is parent and 3 is child. But child is greater than parent. That does not form the MaxHeap property. So I will replace 1 with 3. So 1 will come here, 3 will come here. Okay. So this tree will looks like 4, 3, 2, 1. Okay. In deletion also, what we will do? We will work on only one subtree. We will work on only one subtree. Okay. So we have not changed 2. So at any point of time, we will only do changes in the one subtree. So this is our max heap. Okay. We have deleted 5. Now, what if I want to further delete? If I want to further delete 4. So what will happen? I will delete 4 here and put 1 here. So I will put 1 here. Now check. 1 is greater than 3? No. 1 is greater than 2? No. So I will check. 3 is greater than 2? Yes. So I will swap 1 and 3. Okay. So swap. This will be 3. This will be 1. Now the tree will looks like 3, 1, 2. It is max heap. Okay. It follows the properties of max heap. Now what if I want to further delete 3? So remove 3. Now what I will put? I will put 2 here. Okay. So put 2 here. Now 2 is a parent, 1 is a child, and parent is greater than child. So no need to do anything. Okay. Now further if I want to delete 2, let's delete 2. Now we have 1 at the last index and we have only one element. So 1 is follows the max heap properties. Okay. So this was about deletion. Let's write the pseudo code for deletion also. Basically what we are doing, we are deleting from top and putting the last element at the top, and then we are comparing with the childs. So in childs also we will compare whichever greatest child is there, we will swap with that value. Okay. So let's write our code for deletion. So this is our code for deletion. In deletion, what we will take? We will take last index and we will take our array and we will swap this. Okay. So why we are swapping? We want to put the maximum element to the last index. Okay. That's why we are sorting. So in sorting, what we will do? We will put the element in the last index. So we will put our maximum index in the last index and we'll keep on doing this. Okay. So I will decrement my last index and now I will run this loop. Okay. So I will find my left child, I will find my right child, and I will compare. So first I will check whether our child is in range or not, and then we will check whether my parent is greater than the left child or not. Okay. So if my parent is smaller than left child, then what we will do? We will change our index. So in index, first initially it was I. Okay. Then I will update my index. Now I will check for right child. Right now I am checking for left child. Now I will check for right child. So what we will do? We will check whether the right child lies in the range or not. If it lies in the range, then what I will do? I will compare whether my parent is greater than right child or not. Okay. So if it is greater than right child, okay, what I will do? I will change my index. Initially my index was parent. Okay. So I is the index of parent, right? Now if my left child is greater, then what I will do? I will update the index. Okay. So now index will have my left child index. Okay, that means what? That means my left child is greater than the parent value. Okay, now next I will check for right child. So if my right child value is greater than my parent or greater than my index, what I will do, I will update the index. Okay, so let's say index have the left child. Now index will update to the right child. That means what? Now my index will be right child. Okay, so out of parent, left child and right child, my right child was maximum, so that's why I am increasing it. Okay, so I will update my index. Okay, now I will check my index. My index initially was parent index. Okay, so I stored the parent index. If there is no change in my parent index and the maximum index, then there is no need to swap. Okay, but if I found the maximum in the left child or in the right child, I will swap either from left child or from right child. Okay, we will see example. And now I will update my I. Okay, so my I will be hold index and it will keep on running. Okay, so we have written the code for insertion also. So insertion we have discussed, deletion we have discussed. Okay, now how heap sort will work. First, let's insert some elements in the heap. Okay, so let's say I insert some more elements. Okay, so let's say I insert, it is 10, it is 12. Okay, let's say it is 5, let's say it is 4. So I am inserting these many elements in my heap. Okay, let's run a for loop here. So I have inserted 9, 10, 12, 5, 4 in the heap. Okay, so let's see how these will be stored in the heap. Okay, so let's save it and run it. See, in the heap, my root element will be maximum. Okay, so 12, then left child will be 9, then left child will be 10. Okay, so this is 12 will be at first level, 9 and 10 are the left and right child of 12. So these are at second level, and now 5 and 4 are the child of 9. Okay, so it will be like 12, then 9, then 10, then 5, then 4. Okay, so we know that this is a max heap, right? This is nothing but a max heap, and we have created the max heap. Now I will delete it. Okay, I will delete it. I will perform the deletion operation. So deletion operation, what it will do, it will move the maximum elements. It will move the maximum elements in the last. Okay, so it will start from n-1 index, then n-2, then n-3. Okay, it will keep on decreasing. If I perform deletion operation first time, so what will happen? My first maximum element will be stored at last index. Okay, and let's print it. Okay, let's take a end line. Now let's run this. See, my heap initially was 12, 9, 10, 5, 4. Okay, after one deletion operation, I got maximum element at last index. Okay, so I got 12 at last index. Now if I perform deletion operation one more time, what will happen? I will get second maximum element at second last index. So let's save it and let's run this. See, on first deletion operation, 12 was moved to last index. In second deletion operation, 10 is moved to second last index. Now if I perform this one more time, now my third largest will be stored at third last index. Okay, so let's run this. 9 is my third maximum value. Okay, so 9 is my third maximum element. So 9 is stored at third last index. Okay, so if I do this one more time, now 5 will be set. Okay, so let's run this. See, now 5 is moved to my correct position. Okay, see, in one deletion, first maximum will be moved to my last index. Okay, then I will decrement my count of index. So my last index will be reduced. And now in second deletion, my 10 will be moved. In third deletion, my 9 will be moved. In fourth deletion, my 5 will be moved. Okay, so if I do one more time, then 4 will set to its correct position. Okay, so if I do 5 times, let's run this. See, 4 is set to correct position. So if I set n minus 1 elements to its correct position, then the remaining will be already in correct position. Okay, so I have done 5 times insertion and I have done 5 times deletion. Okay, so this will take how much time? This will take n log n times, right? And this will take how much time? This will also take n log n times. So total my heap sort will take 2n log n times. Okay, so I can write something like this also. I can write in for loop also. So for int I equals to 0, I is smaller than size I plus plus. So I can write in for loop also. Okay, so how many elements we have inserted? We have inserted 5 elements. Okay, so it will run till 5, 0 to 4, 0, 1, 2, 3, 4. So 5 times deletion will be performed. Okay, so if you run it again, we have already sorted our elements. So this is our heap sort. Now you can ask that how we are moving to the last index. Okay, so come in the deletion. See, in deletion we are doing this swap. What we are doing? Array 0 initially contains the maximum element because we are using the max heap. So every time array 0 will contain the maximum element. Okay, and what we are doing? We are moving the maximum element to the last index. We are moving the maximum element to the last index. Okay, and then reducing our index. So this is our deletion and this is our insertion. Okay, now the time complexity it will take, I have already discussed multiple times, it will take order of 2n log n times. Okay, so I hope you understood it. And there is one more way which is better than this. See, in this method, insertion is taking n log n times, but there is one more way which only takes order of n times, order of n time to build the heap. Okay, so we are building the heap in n log n times, but we can build the heap in order of n times. So let's see how we can build this in order of n time. So there is one more method to build a heap called Heapify method. Heapify method. Okay, this is very important in our heap sort, and we will use this Heapify method a lot of times. Okay, so we are performing Heapify method on Max Heap. So we call it as Max Heapify. Okay, if you are performing this on MinHeap, then you can call it as MinHeapify. Okay, so I called it as Max Heapify. So how we can create our Max Heapify method? So how does a Max Heapify works? Let's take an array. Let's say we have 50, 10, 40, 30, 20, right? So Max Heapify says that create a complete binary tree of these elements, okay, without any ordering. So let's say I create 50, then 10, then 40, then 30, then 20. Okay, so I will create a complete binary tree of these elements, right? Now Max Heapify method starts from first non-leaf node. Okay, so this is leaf, this is leaf, this is leaf. Leaf means which don't have any child. So these three are leaves. So first non-leaf is this one. This is first non-leaf from last. Okay, so we will start Max Heapify from here. Now I will compare this with its child. Okay, so first I will compare with left child, then I will compare with right child. So let's compare with 10 and 30. So out of 10 and 30, 10 is small, 30 is larger. Okay, so what we will do, we will take a variable, let's say largest. Okay, so initially I will take 10 as largest. Now I will compare 10 and 30, which is largest? 30. So I will store 30 here. Okay, now compare our largest with right child. So compare our largest with right child. Okay, so right child is 20, largest is 30, so 30 is capital. So I will swap these values. Okay, so it will be 30, it will be 10. Now I will go to further. Okay, I will go further. So after 30 I will go to 50. Now we'll check. 50 left is 30, 50 right is 40. So 30 is less than 50, yes. 40 is less than 50, yes. So this is max heap. Okay, so we have created the max heap. Now the elements are 50, 30, 40, 10, 20. Okay, this is our max heap. So using Max Heapify method, we didn't travel the whole array. We only need to traverse the n by 2 element, right? Because in any complete binary tree, there are n by 2 elements at the leaf. Okay, so there are n by 2 elements at the leaf. So let's write our Max Heapify will start from first non-leaf node from end. Okay, our Max Heapify method starts from first non-leaf node from end. So it will run for almost n by 2 elements. N by 2 elements. Okay, because any complete binary tree have almost n by 2 elements at the leaves. So we are not counting the leaf elements because we are not running our Max Heapify on leaf elements. Okay, so this will run for n by 2 elements. We don't need to run it for n elements. Now Max Heapify method takes how much time? Let's see. So at max what can happen? Let's take one example. So let's say it is 10, it is 20, it is 30, it is 40, it is 50, it is 60, it is 70. Okay, so we will start our Max Heapify method from first non-leaf node. Okay, so this is leaf, this is leaf, this is leaf, this is leaf. This is first non-leaf. 30 is first non-leaf. Okay, so I will compare 30 with 60. 60 is largest is 60. Now I will compare largest with right child. So 60 and 70, which is largest? 70 is largest. So I will swap it with 70. So I will swap 30 with 70. This will be 70, this will be 30. Right? Now this part is sorted. Okay, 70, 60, 30. This is following the properties of Max Heap. Now come to this. So 20. Let's take largest as 20. Now its left child contains 40. So I will update my largest will be 40. Now come to right child. So right child contains 50. So now I will update my largest as 50. So it will be 50. Okay, now after traversing left child and right child, I will update. So this will be 50, this will be 20, right? So this part is also sorted. This part is also following the properties of Max Heap. Now come here. So now let's take largest equals to 10. Okay, and left child contain 50. Its left child contain 50, and I will update my largest. So largest will be 50. Now move to right child. So its right child contain 70. Okay, so I will update my largest as 70. It will be 70. Now after traversing left and right, I will swap. So it will be 10, it will be 70. Okay, at max there will be log n swaps, right? So at max there will be log n swaps, right? So each Heapify method takes log n time, not equals to log n times, but upper bound. In upper bound it takes log n times, because at every time, see, we are not running it for leaf nodes. Okay, so it will be rare that it will run for log n times. In some of the cases it will run for log n time. Okay, so building max heap using max heapify will take how much time? Will take, we are running it for n by 2 elements, right? N by 2 elements, and each max heapify method take how much time? Order of log n times. Okay, so it will be how much? It will be n by 2 order of log n times. So it will be nothing but n log n times, right? So building max heap will take order of n log n times. It seems like it will take order of n log n times, but by derivations, it is proved that it takes order of n time. By derivation, it is proved that it takes order of n time. Now you can see the derivation on different websites. Okay, so let's say we have this tree. So these elements will take no comparisons, right? So these elements will take no comparison, and this at this level there can be only one swap, right? There can be only one swap. At this level there can be two swaps, at max two swaps, right? At this level there can be 1 2 3 swaps. Okay, so if we write the equation, it takes almost order of n times, right? After calculating with the equation, it takes order of n times. So build heap using Heapify takes order of n times, and initially what we are doing, we are taking order of n log n times. So we have reduced, right? But in deletion, what happens? We will delete all the elements, right? So in every deletion we will get one maximum element, then one maximum. Okay, so we will get largest, then second largest, then third largest, then fourth largest, till our last element. So deletion using max heapify will take n log n times for n elements. Okay, we have discussed heapify takes log n times, right? Now deletion, we will delete n elements, so it will take n log n times. So the total time complexity using this method will be, build heap will take order of n times, and deletion will take order of n log n times. So it will be nothing but order of n log n times. So heap sort, in best case, in worst case, in average case, it takes order of n log n times, right? So let's write a pseudocode for Heapify method. I will take largest as I. Now what I will do, I will take my left child and right child index. So now I will check. So my largest will be L. Okay, if my right is less than my size and my array at right is less than array at largest index, then I will update my largest. So my largest will be R. Okay, and what I will do, I will check if I have updated the largest or not. So what I will do, I will swap. Okay, and I will call the MaxHeapify again. I will call the MaxHeapify again for lower elements. Okay, so I will call MaxHeapify for array, and now I will call it for my largest. Okay, so this is our pseudo code for MaxHeapify, right? Let's code it and let's see. Okay, so let's write our code for heap sort. Let's say I'm taking only 10 elements. Let's say 10, 20, 40. Okay, so let's write up our Heapify method. Heapify method. Okay, so let's write our code for Max Heapify. Max Heapify. Okay, I will take an array. I will take the size. I will take the largest as I. So largest is I. I will take left child. So let's say left child equals to left. It will be 2 into I plus 1. I will take right child. So it will be 2 into I plus 2. Now what I will do, I will check if left is less than my n and array at left is greater than array at largest. So what I will do, I will update my largest. Largest will be equals to or left, right? Now check my right is less than n and array at right is greater than array at largest. Then what I will do, I will update my largest. So my largest will be equals to right. Okay, now I will check if my I does not equals to what, my largest, right? That means we have updated our largest. So what I will do, I will call my swap. I will call my swap for array of I comma array of largest. Okay, now I will call my max heapify for remaining elements. We will call max heapify again. Why? Because it may happens that after swapping the elements order get changed. Okay, so to check that if other elements are not disturbed, so I will call my max heapify. Okay, so I will call my max heapify for array comma n comma largest. Okay, so I will check for lower elements. That's bracket. I will put this bracket, sorry. Okay, so this is our max heapify, right? This is our max heapify. Now I will call my max heapify for building. Okay, so let's call the heap sort here. So let's call the heap sort. I will pass the size. So the size, let's say 10. Okay, now I will create a function name as heap sort. Heap sort. Okay, I will pass array. I will pass the number. Now I will build it. I will build the heap using max heapify. Max heapify. Okay, in time complexity order of n, right? Please check for the time complexity how it is order of n. Okay, so let's run it for, I will call heapify for n by 2 elements. So int I equals to n by 2, I is greater than equals to 0, I minus. Okay, so n by 2 elements are leaf elements. So first non-leaf element will be at n by 2 minus 1. Okay, now I will call my max heapify. max heapify for what? For my array with size n and my I. Okay, so this will build our heap. This will build our heap. Now after building the heap, we will perform deletion operation. So perform deletion operation using Heapify method only. Okay, so we will perform deletion operation for n elements. Okay, so I will call this for int I equals to n minus 1, that is our last index. I is greater than equals to 0, I minus, and I will call my max heapify method for my array. Okay, array of I comma 0. So it will run till 0. Okay, let's save it and run this. Okay, 10, 18, 19, 20, 37. Yeah, this is sorted. Okay, so we have done using max heapify. We have solved this using max heapify. So it will take how much time? It will take order of n for building the heap and n log n for deletion operation. Okay, so this is our code for heap sort. Okay, we are calling max heapify. Why? Because we need to update the elements after the swapping. So we will update the elements below our current element. Okay, so from our current element we will go to the bottom. Okay, so this was our heap sort. I hope you understood it. Now there are few more things about heap sort. Let's discuss them also. So heap sort is a comparison based sorting technique. Okay, it is based on binary heap. It is in place algorithm. It is not stable because while swapping the relative order can change. Okay, and we use Heapify method. We have discussed what is Heapify method in heap sort. Okay, so we have discussed all the things, right? So this was all about heap sort, and we have seen how to build heap, how to use max heapify, what are heaps, what is MinHeap, what is max heap. Okay, we have seen how we do heap sort, what is the time complexity, what is the space complexity. So space complexity, it will take order of one space. Okay, because we are not using any extra space. I hope you understood this lecture, and if not, then please revisit the lecture. Heap sort is a bit confusing, but once you understand it, it is quite easy. Do more try run, take more examples, do more try run. It is very easy to understand. Okay, so do more try run, take 4-5 examples and do try run. You will easily understand it. Okay, so this was all about this lecture. Let's meet in the next lecture. Till then, bye bye, take care.